This is problem 313. This is a three-dimensional problem that we want like to analyze the equilibrium of the system. And we are asked to find the tension of this core and the tension in this pole if we are carrying a weight of 400 pounds. So this pole is carrying a crate. You can see it in the figure. I just draw the equivalent weight, and it's held by two cords. So the first thing that we always have to do is draw our free body diagram, right? So the free body diagram, I will draw the free body diagram of point A. So my point A, right here, I have a active force, which is the 400 pounds, which is active, and then I have the reactive force caused by the support that is carrying the weight. So I have two cords. Let's call this core DAC and this core DAB. And then we have this pole. Since you see that this pole is subjected at point D and is pulling down, the reaction will be against the point A. So we are pulling this. So these two cords are pulling the pole, and the pole is being compressed. Since the pole is being compressed, I will just draw a reaction. I'm going to call a reaction, and I will call it A, B. So these are my free body diagrams. Of course, I don't have any angles, but I have all the information about the direction of these forces in this diagram. In order to apply my equations of equilibrium, the first thing that I have to do is put these four forces in terms of the components. So I have this is the x-axis, this is the y-axis, and this is the z-axis. So I draw my axis over here. So this is the x-axis, this is the y-axis, and this is the z-axis over here. So let's draw the components. The first one, always the weight is very easy. So this a vector is 400 pounds in the negative direction of K, because K is my vertical direction. Then I have to draw the vector, the direction for the reaction AD. This is a vector. That reaction AD has a magnitude and a direction. Let me call it, I can call it U, or I can call it lambda AD. And this is a unit vector. You see that my notation to differentiate a vector of a unit vector. The unit vector is have only information about the direction, because the magnitude is right here. So how do we find this unit vector? As you recall from the theory, a unit vector will be equals to, let me give myself a little bit more space. Unit vector will be equals to the vector, in this case will be from D. Actually this vector goes in this direction, so I should call it, if I want to make sure that I also take into consideration the direction, let's fix our name. I mean, it's not, names are whatever, but in order to make it easy for our mind not to make a mistake, I'm going to call it DA. So I know that this, I said that my positive direction is from D to A. So DA, so DA, and then I will do the vector from D to A over the magnitude of that vector. As I say, that just make it easy in the direction. It will not be wrong if you guys name it this vector in the opposite direction. You just will get a negative value. So how do we have the dimension of this vector? Well, as you recall, we can either subtract the coordinates of the vector or just go graphically. How do we recover this vector? So from D, which is 0, because it's at the origin of our coordinate system. I go in x, I don't cover any distance because the point is in the plane YC. So I go 0 in x, 6 in y, and 2.5 in k over square root of 6 squared plus 2.5 squared. That gives me a value of, I have it right here, this one right here is 6.5. So that will be 6j plus 2.5k over 6.5. If I want to avoid having decimals and make my coordinates, my system of equations a little bit easier to solve, I can actually right here multiply the numerator and the denominator by 2, and I will have 12j plus 5k over 13. So it will give me that dA will be equals to the magnitude times my direction. Okay, so let me just make sure that that's where we are going to be where we need for our equation of equilibrium system. So we got this one right here, and we got this one. Let's do the other two very similarly. So this one right here, the AB as a vector will be equals to DAB magnitude times the direction AB. That will be equals to DAB, and this one right here will be equals to the vector AB over the magnitude of that vector. That will be equals to the vector AB. I can do it, as you recall, subtracting the coordinates of B minus the coordinates of A, or I can do it by covering the distance. So in X, what do I have? I have -2 in I. In J, I have -6 in J. And in C, I have 4 is point B, but A is already at 2.5. So I have to subtract 4 minus 2.5. That gives me 1.5 in that positive direction. Over the magnitude of that vector, which is 2 squared plus 6 squared plus 1.5 squared. That gives me the AB. Get this square root, that gives me again 6.5. So I will multiply the vector in the numerator and in the denominator by 2 so that I don't get any decimals. So at the end, I will write the result that gives me that the vector AB is equals to the magnitude times this vector. And this vector gives me -4 in I, -12 in J, plus 3 in K. Remember that I multiplied everything by 2, divided by 6.5 times 2, which is 13. So this is the other vector that I need. And the last one is the AC. The AC will be TAC times the unit vector, which is the unit vector from A to C. And it's very similar process I will do in this case. In X, I will go 2 positive. I will go 6 negative in J. And in K, I go 5.5 minus 2.5. That gives me 3 positive. And this is over the square root of 2 squared plus 6 squared plus 3 squared. And that gives me, this gives me a 7. So that doesn't give me any decimals, so I don't have to multiply by 2. So that gives me AC equals to, as a vector, AC that multiplies 2 positive plus negative 6 in J plus 3 in K, all divided by 7. Okay, so I got my last vector in components. So I got this vector, this vector, this vector, and this vector. Now, with the little space that I have, I will do my equations of equilibrium in 3D. That means my adding forces in X, adding forces in Y, and adding forces in Z. So, what forces do have components in X? So this one doesn't have any component in X, this one doesn't have any components in X, so I have only this one and this one have components in X. So my first equation will be negative 4 over 13 TAB plus 2 over 7 TAC equals 0. That's my first equation. My second equation will be the components in J. This has component in J, this has component in J, and this has component in J. So it will be R 12 over 13 positive R dA minus 12 over 13 DAC. This requires a lot of attention so that we don't make any mistakes, right? Minus 6 over 7 DAC equals 0. And the last equation have the K components. This has a K component, this has a K component, so all of them. So I have 4 components in my equation. So that will be equals to negative, let me start by this one right here. So it will be positive. It will be 5 over 13 RDA. This one over here is positive as well. Positive 3 over 13 DAB. This is positive as well, plus 3 over 7 DAC minus the weight that I want to carry equals to 0. So I was able to get 3 equations with 3 unknowns. And solving the system of equations I get the result. So, well, as you know, well, you plug in one equation, one variable into the other one, and so forth, and I have the values right here. I have that DAB is equals to 274 pounds. Then I have DAC is equals to 295 pounds. And the reaction AD, or DA I call it, DA is equals to 547 pounds. In case that we would have wrote the arrow of this reaction in the other direction, we will have a negative sign in front of that reaction. Please remember that the tension of the cores are always in the direction of where what we are holding to where they are supported in the wall, because the tension of the cores do not push, they only carry tension, they only work in tension. But this pole over here can work in tension or compression. So this is the solution of this problem.